Welcome. In this video, we're going to talk about part one of the fundamental theorem of calculus. This really is the benchmark rule for everything we've been learning this semester. So the idea here is if we have f, a continuous function on a closed interval a to b. So we have a continuous function closed interval. So we have some new notation to think about. We have this capital F. What does capital F represent? Capital F, the way we've talked about it, represents the antiderivative. So the antiderivative is the derivative, d dx, of the integral from some constant a, the lower bound, up to some value x, which is variable, of f of t with respect to t. So that would also be continuous on a to b, and it would be differentiable everywhere inside the interval. And the derivative, so what does that mean? We have the derivative of the antiderivative. The derivative of the antiderivative, well, that's what we have here, the derivative of the integral, the antiderivative. What is it equal to? It is equal to the original function f of x. So notice in here, this was f of t integrated with respect to t. And what variable plugged in for x? That x variable upper bound. So variables can change within these problems as well, but generally it's set up with f and t. And really what we're emphasizing here is that the derivative of the antiderivative is the original function. So what does that mean? How can I use the fundamental theorem of calculus to solve a problem? Well, we need to determine in this next problem using fundamental theorem of calculus dy over dx. We are given y and it's represented as some integral. We have the integral from lower bound variable x to an upper bound constant. My f of t is 3t sine t integrated with respect to t. So that matches what we have up there in our definition. What doesn't match? We only have the integral symbol. So in order to create this or make this look like what we have up above, I need to differentiate. I need that derivative with respect to x. I need that in front. So in order to do that, I'm going to differentiate the function. So d dx of, and we have y equals the integral from x to 5 of 3t sine of t dt. So on the left side, that integral value becomes dy dx. And then on the right, I have d dx of the integral from x to 5 of 3t sine of t dt. So now I ask you again, does this look exactly like what we have up there? So the order of those bounds is very important. My lower bound is constant. My upper bound is variable. What happens if I switch the two bounds here? Well, remember, when we switch bounds, we negate the integral. So I have dy dx equals negative, as a constant multiple, -1, d dx, and that's the integral from 5 to x of 3t sine of t dt. So the derivative of the integral, that means now I can take this x value and plug it in for both of my t's because it's exactly what I have. So I have dy dx, the negative hangs out in front, and this notation, this matches exactly what we have up there. So we can turn that into f of x. In this case, that would be 3x sine of x. And that is basically how we interpret or read the fundamental theorem of calculus. So it's really about just understanding the notation and manipulating it to solve the problem or to get the piece that you're looking for. So in this instance, we were looking for the derivative, and when I differentiated y, the right-hand side of the equation turned into part 1 of the fundamental theorem of calculus with just a little bit of manipulation. So as you continue to move through your calculus sequence, occasionally you're going to see problems show up that are going to be presented in this form, and you need to know this definition and be able to come back and reference what it's talking about. And the largest part of this definition that we want to understand is that the derivative of the antiderivative represents the function. That's our layman's term idea for what we are learning here. Please let me know if you have any questions. I'm always here to help.